Chapter 11, Universal Gravitation and Satellite Motion. This lecture will help you understand how to calculate what your weight would be on various planets, express how objects are able to orbit the Earth, and determine the connection between orbiting the Earth and being in free fall. The inertial mass of an object relates to the net force acting on it to its acceleration. The gravitational mass of an object appears in Newton's law of gravity and determines the strength of the gravitational attraction. The assertion that the two masses are the same is called the principle of equivalence. An object of mass m sits on the surface of planet X. According to an observer on the planet, the gravitational force on m should be the mass times the acceleration of gravity on that planet. According to Newton's law of gravity, the gravitational force on m should be g times the mass of the planet times the mass of the object divided by the radius of the planet squared. The two forces are the same as little g, and it's equal to big G times the mass of the planet divided by the radius of the planet squared. Planet X has free fall acceleration of 8 meters per second squared at the surface. Planet Y has twice the mass and twice the radius of the planet. On planet Y, G is equal to 2 meters per second squared, 4 meters per second squared, 8 meters per second squared, or 16 meters per second squared, or 32 meters per second squared. The answer is B, 4 meters per second squared. We can see from proportional reasoning that the gravitational force must be 1/2, giving us 4 meters per second squared. We can calculate the acceleration of gravity at various locations. At the surface, the acceleration of gravity is 9.83 meters per second squared. At the top of a mountain, we see a small decrease. At the altitude of the Space Shuttle or International Space Station, the acceleration of gravity drops to 8.9 meters per second squared. Communication satellites are 35,900 kilometers above the surface of the Earth, and the acceleration of gravity is 0.22 meters per second squared. Astronauts on the International Space Station are weightless because A, there's no gravity in outer space, B, the net force on them is 0, C, the centrifugal force balances the gravitational force D, G is very small, although not 0, or E, they are in free fall. The answer is E. The astronauts are in free fall. A circle is the special case of an ellipse. If a small mass m orbits a much larger mass m, the small mass is called a satellite. The speed of a satellite in a circular orbit can be found by balancing the centripetal force and the gravitational force. Doing so, we find the speed of an orbiting object is the square root of the gravitational constant times the mass of the planet divided by the radius of the orbit. According to Kepler's third law, the square of a planet's orbital period is proportional to the cube of the semi-major axis. The speed of a satellite in a circular orbit is the square root of the gravitational constant times the mass of the planet, r star, divided by the radius of the orbit. The speed of a satellite in orbit is also the distance traveled, which is 2 pi times the radius, the circumference, divided by the period, capital T. Equating these two definitions, squaring both sides, and solving for t squared gives a general statement of Kepler's third law, where the period squared is proportional to the radius of the orbit cubed. If we use units of years in astronomical units, we get exactly Kepler's third law. All of Kepler's laws can be derived from Newton's law of gravitation. If the kinetic energy of an object of mass m launched from a planet of mass big M and radius r were equal in magnitude to the potential energy, then in the absence of friction, resistance, it could escape from the planet. We call this the escape velocity or escape speed. For the Earth, escape velocity is 11.2 kilometers per second. This means any object launched from the Earth with a speed of 11.2 kilometers per second or greater will not come back to Earth. Two satellites have circular orbits with the same radius. Which has a higher speed? A, the one with more mass, B, the one with less mass, or C, they have the same speed. Answer is C, they have the same speed. The speed of the orbit depends upon the radius of the orbit, not the mass of the orbiting body. Two identical satellites have different circular orbits. Which has a higher speed? A, the one in the larger orbit, B, the one in the smaller orbit, or C, they have the same speed. Answer is B, the one with the smaller orbit. An object closer to the parent body must move faster to maintain its orbit. A small supply satellite needs to dock with the International Space Station, the ISS. The ISS is in a near circular orbit at a height of 420 kilometers. What are the speeds of the ISS and the supply satellite in its orbit? Despite their different masses, the satellite and the IS travel side by side with the same speed. They are simply in free fall together. The radius of the orbit is the height above the surface, 420 kilometers, plus the radius of the Earth, 6,370 kilometers. The radius is then 6.79 times 10 to the 6 meters. We just found the radius. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and we know the gravitational constant. Substituting these values into the orbital speed equation, we find a speed of 7,660 meters per second, which is about 17,000 miles per hour. When solving gravitational problems, this table provides useful astronomical data for the Sun, Moon, and the planets of the solar system. In recent years, astronomers have discovered thousands of planets orbiting nearby stars. These are called extrasolar planets. Suppose a planet is observed to have a 1,200-day period as it orbits a star at the same distance that Jupiter is from the Sun. What is the mass of the star in solar masses? One solar mass is defined to be the mass of the Sun. We will use the general form of Kepler's third law. We know the period as 1,200 days, which is a little over 100 million seconds. The radius of the orbit is the same as that of Jupiter, which from the table is 7.78 times 10 to the 11 meters. The gravitational constant is known. Rearranging Kepler's third law and solving for the mass, then substituting the known values, gives a mass of 2.59 times 10 to the 31 kilograms. Since the mass of the Sun is 1.99 times 10 to the 30 kilograms, the star has a mass of 13 times the mass of the Sun. A satellite has an elliptical orbit with the Earth at one focus. Which statement is true about the satellite's speed at point A and point B? the speed of point A is greater than the speed of point B, the speed at point A is equal to the speed of point B, or the speed of point A is less than the speed of point B. The answer is A. The speed at point A is greater than the speed at point B. Using Kepler's second law, we find the closer the object is to Earth, the higher the orbital speed. Who discovered 3 laws governing planetary orbits? Newton, Kepler, Faraday, Einstein, or Copernicus? Answer is B, Kepler. Answer is E, the ellipse. The gravitational force between 2 objects of mass m1 and m2 that are separated by a distance r is A, proportional to r, B, proportional to 1 over r, C, proportional to 1 over r squared, D, m1 plus m2 times g, or E, m1 plus m2 times big G. The answer is C, proportional to 1 over r squared. Newton's gravitational law is a 1 over r squared force. The value of G at the height of the space shuttle's orbit is 9.8 meters per second squared, B, slightly less than 9.8 meters per second squared, C, much less than 9.8 meters per second squared, or D, exactly 0. Answer is B, slightly less than 9.8 meters per second squared, due to its increased orbital radius. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. What is the gravitational force exerted between an electron of mass 9.11 times 10 to the minus 31 kilograms and a proton of mass 1.67 times 10 to the minus 27 kilograms in a hydrogen atom where the distance between the electron and the proton is 5.30 times 10 to the minus 9 meters? Pause the video to work on the problem. Using Newton's law of gravity, the answer is 3.61 times 10 to the minus 51 newtons. Find the orbital velocity for Uranus as it orbits the Sun. Pause the program to work on the problem. Using the speed of an orbit formula, the answer is 6,800 meters per second. Find the time Saturn takes to orbit the Sun. Pause the video to work on the problem. Using the general form of Kepler's third law, we find a time of 9.32 times 10 to the 8 seconds, or about 29.6 years. Your assignments are to read Chapter 11 in the textbook, and your homework assignments are due April 6th.